We're ready. All right. So today we're continuing with the mathematics behind rheology that we need. We've been studying just vector and tensor mathematics. So as you saw in the homework, it's something you've seen before in many ways. But I want you to learn how to speak in this vocabulary because later, as I said, we're going to take off into the wild blue yonder and we need to be speaking the same vocabulary. So last time I went over some definitions and I introduced to you the tensor. So let's just review those tensor lecture slides and see how it feels second time through. The tensor we defined as an indeterminate vector product and as a linear vector function. And then we defined these various new operations. One is the scalar product of two tensors, which we learned was written as this colon, and it involved dotting the two nearest unit vectors and then the two furthest. But that's all we needed to know was that definition, and then we could use our usual Kronecker delta notation and get the final result very easily. I showed this derivation of a linear vector product, saying that a tensor was a way of expressing a linear vector function. So here's a vector function. If we add to that function the properties of linearity listed here, which are that if I take f of lambda x, I can pull the lambda out and take lambda of f of x. Or f of x plus w, I can apply the function sort of in a distributive way and get f of x plus f of w. And those are unusual properties. We talked about sine, for instance, is not a linear vector function. But with those two properties, we were able to show that a tensor appeared very naturally. And all I did to show that was I wrote a vector in general form, applied f to it, and then used those linear rules. So I brought the a out, and I took the f functionality in a distributive way. And then I was able to show that that was the same as this dot product of a vector and a tensor. So the vector math, the vector manipulations that we've been learning, the vector and tensor ones, are going to allow us to express linear vector functions in a very compact way. We had these definitions, the identity tensor. I'm going to try to be careful to always call things tensors when they're tensors and matrices when they're matrices, but there's some overlap. So for instance, this is the matrix representation of a tensor. Its math works the same way as a matrix, but you can tell it's a matrix representation of a tensor because it has this little subscript here. And this subscript means that these are coefficients with respect to a particular basis. And we saw that in the homework, that we can change the basis with which we write a tensor. The zero tensor would be an exception to that. It always looks like this. And then we talked about the magnitude. So this is one of the invariants related to one of the invariants of the tensor. And vector matrix transpose and how to do that. Definitions of symmetric and anti-symmetric tensors. So this is going to be important when we do rate of deformation because we're going to actually split the rate of deformation tensor into its symmetric part and its anti-symmetric part. And that's going to be very useful to us. And then today we're going to see a little bit more about tensor order. If we go back to dot products, so for instance, A dot M, we had a vector which is of order 1, and a tensor which is of order 2, and the net result was a vector, a matrix, a scalar, a vector, or a tensor? Vector. This gives a vector because there are two unit vectors inside the M, and one of them goes away, but one does not. It gives a vector. So the dot product reduces the order of a tensor. So for instance, when I had A dot B, the result was a scalar, a vector, or a tensor. Scalar. It gave this A sub I, B sub I, which has no e's in it. So that's a scalar. It's just some number. We saw that in the homework. And you see that once again the dot product reduced the order of the vector into making it a 0th order. So this is 0 order. And this was first order, order 1. So order was just this definition of how many components it took to express the quantity in Cartesian coordinates. So our scalars take 1, our vectors take 3, and our tensors, our second order tensors, take 9, excuse me. We're going to see today that we have some operators that increase the order of a quantity. So for instance, del of a scalar is going to make us a tensor. Del of a vector is going to give us a tensor. Del of a tensor, first order tensor, gives us del of a second order tensor gives us a third order tensor. So that's another way that this concept of tensor order is going to come in, and we'll see that today. And then the invariants. So the tensor invariants are defined here. We did a little bit on the homework where we saw that you must take note of this little caveat that we can only use these definitions when the tensor is written, when you're dealing with the coefficients written in Cartesian coordinates. Then the invariant's the trace. First invariant's the trace, the second is the trace of the a squared, the third is the trace of a cubed. So if you have a tensor written in non-Cartesian coordinates and you need to know what the invariants are, you must first transform it into Cartesian coordinates and then take the traces. So now today we're going to talk about these differential operations. Once again, I showed you previously the Navier-Stokes equation, which, by the way, I don't require you to memorize. I just use it a lot. And the Navier-Stokes equation has two types of derivatives in it, a time derivative and this del. Del is everywhere, and the time derivative's in the front. So time derivatives of a vector are very easy. You just take the time derivative of the vector, and you get the time derivative of the vector. If you were dealing with coefficients, so for instance, v1, v2, v3, d by dt, it's just the time derivative of each of the coefficients. If I had a vector that was just numbers, then that time derivative would just be 0, just like regular numbers. And so a vector that's going to give a non-zero is going to have a function in it. So some function of time. So it might be 6t00 d by dt is equal to 600, something like that. So that's easy, taking derivatives of vectors, and tensors work the same way. There are just 9 components, and you take the derivatives, the time derivatives of each component. So time derivative, piece of cake. This is for a scalar, this is for a vector, this is for a tensor. And that's true of individual, say, spatial components that we might take. So the derivative with respect to x1, you can take the derivative with respect to x1 of a vector or of a tensor, and it works just like this time example. But more interesting to us is the gradient operation. So the gradient operation, you learned about in your calculus classes, is defined in a manipulation by these equations that I'm going to go over. What its meaning has to do with what physics you apply to it. But it's the spatial rate of change of a function. And we're going to see its meaning best when we go back and derive, for instance, this Navier-Stokes equation, which we're going to do pretty soon. Okay? And this del operator, we're not going to put it in and say, oh, it's del this, and that's the meaning of it. We're going to start with mass is conserved, momentum is conserved, and it's going to appear the same way that we made the tensor appear when we discussed the linear vector function. So you're going to see how it comes to have its meaning. This term is the rate of change with time term of the momentum balance. This is the flow in minus flow out term. This is force due to pressure. This is momentum transfer due to viscosity. This is force due to gravity. And they're all just going to come from putting that physics into the equation. And we're going to see what del does for us. But before we do that, we're going to learn the manipulation. So that's what we're after today. And this is the deal. Okay? So the nabla or del operator is this upside down triangle. It's an operator. So it's a vector operator. That's different from what we've been talking about so far. It looks like this. It's defined in Cartesian coordinates. Notice that the e's are written to the left. We could write them to the right as well, but that may, and in fact I will later, but for a certain amount of rigor, we write them on the left-hand side so that it's clear that this del operator doesn't need to operate on this unit vector. These partial derivatives are going to operate on things to their right. So I can write it as this sum, or I can write it in sort of a column vector form or a row vector form if I like. In Einstein notation, remember, we can write this as the summation, 1, 2, 3. So there it is written as the sum. And to get it to Einstein, we drop the summation and we get EP d by dxp. So we can apply this operator to scalars, vectors, and tensors. And so this is in these notes, but I think it's a little bit more engaging if I do it again here. So for a scalar, we have nabla, let's say in my notes it's beta, so I can do that again. And in Einstein notation, we write EI d by dxi of beta. So as I said before, we are increasing the order. Beta was a scalar. It's of order 0. And now it has become a vector, order 1. This partial derivative operator acts on everything to its right. That's important. And so what is this? This is a vector. It has 3 components. It has a 1 component, which is d beta dx1. It has a 2 component, d beta dx2. It has a 3 component, d beta dx3. Or we could have written it as d beta dx1 e1 plus d beta dx2 e2 plus d beta dx3 e3. Either way, that's how we write a vector. Now, notice that I can move this quantity on either side of the E. Up here, it was on the right-hand side. Now I've written on the left. It's just a scalar. So I'm free to move scalars wherever I like with respect to vectors. So back to these slides. This is what I just did. The gradient of beta, I can write it this way or as a column vector or in Einstein notation. And the gradient of a scalar is a vector. Now notice this word, the gradient of a scalar field. Okay? What the word field means is that something varies with position. So there would be no need to take derivatives with respect to these positions x1, x2, x3 if the quantity didn't vary with space. So for instance, density would be a scalar field. The density of air in this room varies with position, and so we could take the gradient of the scalar field and get the gradient of the density in this room. Now, before I move on to vectors, let's investigate this phrase. It acts on everything to its right. So let's try this. What's the gradient of alpha times beta? So how do we write the gradient operator? Okay, EP d by dxp, and then we write alpha beta. So it's important not to be confused about scalars and moving them around once differential operations appear. So although these are scalars, so scalars move around, this derivative operator goes with it. So I can move the whole thing over to the left, but I must move them together because that gradient operator needs to act. It acts on everything to the right. So these are now a quantity that are stuck together. So if I want to expand this, either one of these is correct because we can move scalars around, but I have to do this as the product rule. So this is the first times the derivative of the second plus the second times the derivative of the first, EP. Okay, so we have to use the product rule. That comes up quite a bit, right? So we have to be careful with the derivative operators that we make them act, have them operate before you move them around too much. Now this entity is actually something we could move back into this notation, and this is going to come up in the homework. And to do that takes practice. So I can look at this because of my experience and tell you what this is in this notation. This notation is called Gibbs, after John Willard Gibbs notation. And of course, this is Einstein notation. This is Einstein notation. So we've been learning how to go forward from Gibbs notation into Einstein, but you can also go from Einstein back to Gibbs. And you can check me on this later, but this is alpha del beta plus beta del alpha. Actually, that one's not that hard to see, perhaps. All right, back to now moving on to vectors. We can do the same thing with a vector. So this slide is a little bit exhausting even for me to look at, but you'll have it in your notes if you print it out. Let's try doing the gradient of a vector by hand. I think, as I said before, seeing it done will make it seem very clear. Again, del of W, we just write everything out in Einstein notation. So this is d by dxi, ei in the front. That's del. And then W we write using whatever subscript we feel like. So W, J, EJ. Now remember, del acts on everything to its right. Absolutely everything, including unit vectors. And this would bring up why we only do Einstein notation in Cartesian coordinates. Cartesian coordinates, as I discussed before, are constants. Okay? Cartesian coordinates don't change. And I remember the very first day of class, I made a big deal between constants and scalars. Scalars are things of order 0. Constants are things that do not change. Okay? They're not the same thing. Vectors can be constants. In principle, we usually take the acceleration due to gravity as a constant. It's a vector constant. Doesn't change with position, but it's a vector. The speed of a body on which no forces are acting is also a constant. These unit vectors are constant, which means although this operator is acting on the combo, we don't need to do the product rule because this is a constant. So it doesn't change. So just like it's a 2. If there were just a 2 sitting out front, we could just move the 2 off to the left-hand side and continue. So this is the same as, okay, so this business of what gets to move and what doesn't gets a little tricky. Okay, we have this unit vector, and now we have d by dxi wj ej, and they both get acted on by the derivative, but this is a constant. So this constant is irrelevant to the derivative, so this is the same as ei d by dxi of wj ej. So now I've taken it out of the derivative. It's not being acted on by that derivative anymore. And so it's equal to dwj dxi ei ej. W was a vector, and del W is a tensor. The order increased by 1. And this makes sense. What the del operator is telling us is how something changes in space. And the change of a vector in space is very complicated. Okay? You have this vector has x, y, and z components. And we have to keep track of how the x component changes in the x direction, y direction, z direction, how the y component changes in x, y, and z, and how the z component changes in x, y, and z. And that's why it becomes one level higher, one order higher of complexity. We can also look at it the way I showed it on this slide without any Einstein notation. So here I've just distributed the del operator across W, okay? Just multiplied the W through. And then I'm taking these derivatives. So now I write W in arbitrary coordinates, and here it is in that position. This one is this, and this one is this. And then I got to do all that distributing of this derivative. So I'm getting 9 terms, 1, 2, 3, and that's these 9 terms, which we can organize the way I just showed, much easier. Del W is equal to the double sum Ej Ek of dwk dxj. Once we've got this derivative sorted out, we can write it on either side of the constant unit vectors. Now, we have also the option of dotting del with a vector. Let's try that using Einstein notation. So we have del dot W. We already know how to do this. We just have to be careful. Okay, the del we write as ei d by dxi dot, and then the W we write however we feel like it, WP EP. I'm choosing P. The del operates on everything to the right, and the dot operates between the unit vectors. Okay, so the del operates on the W and the E, but the E is a constant. So this is the same as ei d by dxi of WP dot EP. And the dot, the scalar doesn't matter with this dot. It can move out to the left. The dot is between the two unit vectors. And this one we know how to do. This is delta IP. I becomes P. And we get d by dxp wp. Done. All right? This was a vector. When we del dotted it, we got a vector, a scalar, or a tensor.
Scalar.
Scalar. There are no e's. It's a scalar. This is just d by dx1 w1 plus dw2 dx2 plus dw3 dx3. This is called the divergence operator. And that comes into the mass balance. So del dot a vector is the del operator, the nabla operator, dotted with the vector written in arbitrary components. When you distribute it and simplify, you get dwi dxi in Einstein notation. Notice that we took a vector, it became a scalar. The divergence of a vector field is a scalar. So once again, I'm emphasizing on this slide how these unit vectors are constants. So this is a constant, this is an operator. This constant can move around because it's not affected by the operator. So the divergence operation decreases the order of the entity. So if we take the divergence of a tensor, we expect to get a vector. So let's see if we do. So del dot the tensor C, EI, d by dxi, dot C, CPM, EPEM. This del is going to operate, this operator only operates on the C because these are constants. And so in this dot product, it acts between the two nearest unit vectors. So this is delta IP, I becomes P, d by dxp, CPM, EM, which is in fact a vector. So that worked out. What vector is it? It's a vector where the m equal 1 component is dcp1 dxp, so it's a summation 1 to 3. The m equal 2 component is dcp2 dxp, and the m equal 3 component is dcp3 dxp. This appears in the Navier-Stokes equations, del dot tau. Excuse me, not in the Navier-Stokes, but rather in the Cauchy momentum equation. We can get even fancier. Del dot del a vector, the Laplacian operator. All we need to know now is this Gibbs notation definition, and we can figure this out because we've got all the rules that we need. This is the gory details. All right? This is the answer, but let's get to it ourselves. Starting right off in Einstein notation, let's take the Laplacian del dot del W. How shall we start? Help me out. Yep.
Let's see here. It'll be E M delta over delta x I.
M. Keep the same one.
Dot E N delta over delta x n.
Right.
And that's a vector, so let's see here, W, PQ.
It's a vector, only one.
P, EP.
Right. There we go. So we've got a couple things to do. We have derivatives, which act on what goes to the right. The derivative of W. We could ignore the e's because they're constants. And we have a dot product. The dot product is going to happen between the two nearest unit vectors. So delta mn, m becomes n. So we can do that one first. We get d by dxn, d by dxn, WP EP. So there's a summation over n and a summation over p. Is this quantity a scalar, a vector, or a tensor?
Vector.
It's a vector. There's one e. That means it's a vector. Okay? This is the second partial derivative of w. Okay? When we do d by dx of v, that's the second partial derivative of v with respect to x. That's what this is. Okay? So this is, let's do the p equals 1 component of this vector. It's the summation n equals 1 to 3 of d by dx n partial WP, like this. Excuse me, W1. So this is equal to second partial W1 with respect to x1 squared plus second partial W1 with respect to x2 squared plus second partial W1 with respect to x3 squared. The p equals 1 means that there's a 1 in each of these numerators. N is summed over, means it goes from 1 to 2 to 3. Each of these individual terms can be written out like this, but this is our more standard notation. So this is the one component. Well, how would the two component look different from this?
Subscripts on top.
The subscripts on the W would be 2, right? And this would still go 1, 2, 3. For the 3 component, the subscripts on top would be 3. 1, 2, 3. This appears in the Navier-Stokes equation. So here's the Laplacian of the vector v. Again, here are all the gory details. Here's the answer we just got. The one component has W1s in the numerator and 1, 2, 3 in the denominator. The two component has W1s in the numerator and 1, 2, 3 in the denominators. And these are added. All right? Remember, we asked ourselves, is this a vector, a tensor, or a scalar? And we said it was a vector, right? This is a vector. This is the most common mistake at this early stage, is to look at this and think it's a tensor, right? It looks kind of like a tensor because there are 9 things. But these plus signs are totally a different story. Okay, so this is a single scalar, this is a scalar, and this is a scalar. It just happens to be the sum of 3 scalars. Very common mistake. Even in my own notes, when I taught this course, I would sometimes forget. I'd be so concentrated on doing the 1, 2, 3 and the 1, 2, 3 correctly that I'd forget the plus signs. So I know that this is an easy mistake to make. So we could do this all over the place. We can't take the divergence of a scalar because there's nothing to dot the del with. There's no e's over here if I just have a scalar. So this one doesn't exist. Remember also that divergence reduces the order of a quantity. So once you're at order 0, you can't go any lower. On a scalar, we can do it. We can do a Laplacian. We cannot do a divergence. Because Laplacian doesn't change order. Going back one slide, the Laplacian of a vector gave us a vector. So the Laplacian of a scalar is going to give us a scalar. Tensors, we can do gradients. Divergence, we can do on tensors. Laplacian, we can do on tensors. Maybe we'll try one tensor operation. Let's try the gradient of a tensor. We didn't do that already, did we? No. Or did we? I did something with C. Oh, I did the derivative, I think. Oh, no. I did do del dot C. So let me do, let's just do del C. Tricky. So this one, again, we just write this one. I usually write it as d by dx p EP. I usually write the E on the second side. It's just a habit, I suppose. So you'll probably catch me doing that quite a bit. And then C, we just write it our usual way, CM I EM EI. There are no dots to carry out, but this operator acts on the C, so this is d by dxp of CMI, EP, EM, EI. This is a third order tensor. Very complicated. In fact, do you remember in your cross product when you learned how to carry out a cross product? A cross B. You learned maybe that it was something times this quantity epsilon, where if you had, it's A, I, B, J, E, K, epsilon I, J, K. Where epsilon, if they're all the same, it's a 1. If one's a negative, I forget the rule myself. I have it in the book. If they're in the order 1, 2, 3, you get positive 1. If in the order 3, 2, 1, or any permutation of 3, 2, 1, you get negative 1. Or if anything is equal, if I equals J or J equals K, it's 0. This is a third order tensor also. This is the only third order tensor I can actually give you as an example. This is actually technically a third order tensor. We actually will not be seeing any third order tensors, thankfully. If this piqued your curiosity, you can look up the cross product in the book and you'll see the correct definition of that epsilon. Okay, let me get my next, looks like I didn't copy my next slides yet. I'll go get those. Now we move on to curvilinear coordinates, which you're also familiar with. And now we'll see how they work a little bit with the Einstein notation that we've used so far. The curvilinear coordinates are these very common coordinates we use for solving problems in cylindrical and spherical coordinate systems. They are r theta z for cylindrical and r theta phi for spherical. In my notation, I put a little bar over this r because it is different from this one. Don't know if I put the example in here. Let me sketch a little bit there. You'll remember this from calculus class, but when you have a point in an xyz coordinate system, if you write it in the cylindrical coordinate system, the r comes straight out from the z, and then you drop a perpendicular into the xy plane, and then the angle theta comes up from the x-axis, r theta z. In the spherical coordinate system, if you take an arbitrary point, the r comes out from the origin. The phi, the theta is, again, you drop this in perpendicular into the xy plane, and it's the same theta, and the phi goes, is that right? I think I've got that backwards, haven't I? That one's correct? And then this one is the phi? Okay, thank you. So the r's have different meaning, and so just to keep that straight, in the textbook at least, I write it with the r bar. Yes? Other way around? Okay. So it's whatever it is in the textbook. I forget which way, which angle is which. Check the book. I probably have it on my explanation on the next slide. The key thing that we want, that's interesting about these, is we do use these, but we cannot use them with the nabla operator that we just saw. These are orthonormal coordinates, but they're not constants. And I talked about that a little bit before. So in vector tensor notation, if you convert the coordinates from Cartesian coordinates into, let's say, cylindrical coordinates, you know you can get these geometric variations, these geometric relationships to relate the unit vectors in the xyz coordinate with the r theta z coordinate. That's just a matter of geometry. Once you've derived these geometric relationships, you can take a vector written, you can take the nabla operator, which is defined and written in Cartesian coordinates, and convert it into how it acts in r theta z coordinates. And there's just a lot of algebra involved. And this is why you've always used tables for getting those various expressions. So for instance, for people who took fluid mechanics from me, you'll recognize this sheet. This is my handout for the continuity equation and the Cauchy momentum equation, and on the other side, the Navier-Stokes equation. This is, it's going to be a little bit hard to see. I can see Jeff trying to make it a little bit bigger for you. But you can print this off the web page to get the details. But you've always used this kind of a tabulation to get things in x, y, z, r theta phi, or r theta z and r theta phi coordinate system. And the reason is we can easily, through the manipulations we've been learning, write, for instance, this continuity equation. If we know it in Gibbs notation, we now know how to write it in this coordinate system. In fact, maybe you'll even recognize this term is just del dot v. We're going to actually do that ourselves. This term is v dot del rho. So if I gave you the continuity equation as d rho dt plus v dot del rho plus rho del dot v equals 0, you're now able to write this out. You don't need this table anymore for Cartesian coordinates. And the same is true down here for the Cauchy momentum equation. This is rho dv dt, v dot del v. Right? So if I gave you that, which I always will, by the way, I don't expect you to memorize it. This is v dot del v plus del p, that's the gradient of a scalar. This is del dot the tensor tau plus rho g. Okay? So once again, you don't need this handout anymore. So let me write that. Let's see, do I have any space? I have a little bit of space here. These three are all d rho dt plus v dot del rho plus rho del dot v. These three equations are rho, this is the one I've been writing over and over again, dv dt plus v dot del v equals minus grad p minus del dot tau plus rho g. So you don't need this kind of a table anymore, or tables in any books, to write it in Cartesian coordinates. This second set, which is really way too small to see, but again, I'm mostly showing it for those of you who've seen these sheets before, okay? These part of the table are complicated, and I'll copy one of the terms down. If I look closely at the cylindrical coordinates for the continuity equation, it looks like this. So it's d rho dt plus 1 over r d by dr of rho r vr plus 1 over r d by d theta of rho v theta equals 0, which is d rho dt plus del dot rho v equals 0. So this is Gibbs. Gibbs is easy to understand. You could write this out for me, I think, now in Cartesian coordinates. You just have to take this dot product that we just learned how to do. You have to do the product rule. First times the root of the second, second times the root of the first, once you've got the scalar coefficients. But it's not that difficult. But where did this come from? Where did this come from? Where did this r in the middle of this thing come from? And the answer to that is, when you put this del operator on this vector in Cartesian coordinates, the vectors, if I write this, excuse me, not in Cartesian coordinates, when I do it in Cartesian coordinates, everything was fine, because x, y, and z, ex, ey, ez, constants, they just were not affected. When I write v as VR ER plus V theta E theta plus VZ EZ, and I operate this del on it, no problem when I get to the EZ, because EZ is still a constant. But when I operate it on ER changes with position. When I operate it on E theta changes with position. And those extra operations when del operates on this vector in this coordinate system leads to these extra terms. Okay, that's where they come from. So if we go back to these slides, that's what I'm doing here. I have del dot v, the continuity equation, or the divergence of a vector v. It's del dot, but if I write v in cylindrical coordinates, I could write this in cylindrical coordinates too, but it wouldn't change the problem. These unit vectors, these two, look what they're equal to. They've got cosine thetas in them, and theta's a variable. So when you take various derivatives, spontaneously these other types of terms appear. So here's what's going on. If you take the nabla operator and carefully, using these relationships on the previous slide, carefully and correctly do the kind of transformation that we did on the homework, where you substitute them in, okay? This you can solve, just like we did with the A and B vector, we can solve for x and y, ex, ey, and ez. In fact, this looks somewhat similar to the one from the homework. We can solve for them and then plug them in here. If we do that, we can write the nabla operator in cylindrical coordinates, and one strange thing appears, this 1 over r. If we then take that written in cylindrical coordinates and operate it on v, we can do that. It distributes the same way. Here it is distributed out. It has to distribute again. This del, this d by dr, has to distribute again. But it has to, you have to take into account that these are variables, these two. And you have to do all that math. So one example of that math is here. This term, if I distribute this term, it's e theta times 1 over r d by d theta, 1 over r d by d theta. And I'm distributing it, and I'm only looking at the first distribution, VR, ER. So that's e theta, 1 over r d by d theta, dot VR, ER. And we carry that out. And I see I've run out of time. So when we carry that out, I'll show this again on Monday. We end up with a product rule. We end up with algebra to do. And we get a very interesting answer, which has to be done for each of these 9 calculations. Okay? That's the algebra behind those tables, which is why we've always been much happier to do the tables than the algebra all these years. And we're going to use the tables in this class too, not to worry. But now we see exactly where they come from. Okay, done. So have a good weekend. I've halfway graded the homework, so I'll have them back for you on Monday.